So in this video, we're going to talk about how to model continuous exponential growth and decay. So exponential growth and decay can be used to model natural events like population growth and radioactive decay. So what happens in these situations is you have continuous growth and decay, and there's a constant E that can be used to help us model these processes. So E is a number called Euler's number. It's actually named after a very famous mathematician, and you can kind of think of it like pi because E is representing a specific number. It's a constant that's approximately equal to 2.178288183, and just like pi, the digits go on forever. So we see E being used in exponential growth and decay formulas that actually model continuous change. So here's a formula for continuous exponential growth and decay with E. So you can see this is very different than our A times 1 plus or minus R to the T formula. So this actually has the values n and n naught. So this is the final value that we're always trying to find. And naught is the initial. So this is like our starting point. This constant e is going to be the base of our exponential function. And then the exponent is going to be k times t. K is the growth or decay rate. And then remember, if it's given to us as a percentage, we have to convert it to a decimal. And the way we know if we have growth or decay is that K will be positive when we have growth and K will be negative when we have decay. And as always, t is going to represent time. So let's try this example. Suppose that the population of a certain country grows continuously at an annual rate of 2%. If the current population is 3 million, what will be the population in 10 years? So the key that we know that we need to use this formula is this word continuously. So we're going to use this n equals n naught e to the kt and then use that to solve this problem. So n naught is going to be our starting value. So here it tells us that the current population is 3 million. So that's going to be our starting value. So the value of K is going to be the growth rate. So it's given to us as percentage, right? So it's 2%. So we're going to convert that to a decimal. So that's going to be 0.02. Then it says the value of T, which is time. So it's asking us for the population in 10 years. So that's going to be our value of time. So we can use now this formula n equals 3 times e to the 0.02 times 10, and that's going to be our growth formula. So now let's go ahead and go to the Desmos scientific calculator and use that to figure out what this value is. So we do 3, and if you type e, Desmos automatically knows that's Euler's constant. So you can just go ahead and type e, and then you do the exponent button, and we need to put our exponent in parentheses. So we have 0.02 times 10. Okay, so make sure you put that 0.02 times 10 in parentheses, because if you do 0.02 and then times 10, it won't put the 10 in the exponent. So go ahead and hit enter, and it tells us that it's 3.66. But remember, our value is in terms of millions. So if we round this, this is going to be 3.7 million people in 10 years. So now let's try this example. It says, suppose that a certain radioactive element decays continuously at an annual rate of 10%. If you begin with a 200-gram sample of the element, how many grams will be left in 3 years? So once again, we see that word continuously, so we know we need to use this formula. So n naught is the starting value, which in this case is going to be 200 grams. K is going to be the growth or decay rate. So in this case, we know we have decay, so we're going to make our K negative. So this is actually negative 10% because it's decaying. We convert that to a decimal, so that's going to be negative 0.10. T is the value of time, so that's 3 years. So let's go ahead and plug that all in. So we have n equals 200 times e to the negative 0.10 times 3. So now let's go ahead and type this into Desmos so we can figure out what this is. So we have 200 e, and then we do exponent, and then parentheses, negative 0.1 times 3. And when we hit enter, it gives us the value, which is 148.2 grams. So now you can go ahead and pause the video and try doing this example on your own. So in this one, it already gives us the formula, right? We have our growth model. So we have just now to figure out the value of time. So we're going from 2010 to 2050. So that means there's a difference of 40 years. So the formula is 3000 e to the 0.02 times 40. And when we do that on our calculator, we get 6,677 people. Remember, we have to round to the nearest whole number whenever we're talking about people. So, another application of this is to calculate something called continuously compounded interest. So, remember in our previous lesson, we talked about interest that was compounded at a fixed schedule, right? It was compounded monthly or daily or weekly. Sometimes interest is compounded continuously. Okay, so it's not on a fixed schedule. And when we're solving these problems, we need to use this formula. So once again, we see that we have that value of E whenever we have something continuous. And so this is A equals PE to the RT. P is once again the starting value. R is going to be the interest rate, which we could turn into a decimal, and then T is going to represent time. So let's look at some examples. What is the final value of $1,000 invested for 10 years at 5% interest compounded continuously? So that compounding continuously is when we know we need to use this version of the formula. Okay, so we just go ahead and plug it in. So we have P, which is our starting value. So that's $1,000. And then we have our growth rate, which is 5%. So convert that to a decimal and we get 0.05. We have T, which is the value of time. So that in this case is going to be 10 years. And let's plug that all in. We have A equals 1000 E to the zero point zero 0.05 times 10. So when we plug that into our calculator, we have 1000 E and then exponent. And then we put that exponent in parentheses. We have 0.05 times 10. And when we hit enter, we're going to round to the nearest cent, right? Because when we're talking about money, we can round to the hundredths place. So we have 1648 and dollars and 72 cents. Okay, so now you can go ahead and pause the video and try doing this example on your own. So it says, what's the final value of $4,000 invested for 5 years at 3.6% interest compounded continuously? So once again, that continuously tells us we need this version of the formula. So the starting value is $4,000. We take the percentage, that rate, that 3.6% converted to a decimal, we get 0.036, and the time is 5 years. So we have A equals 4,000 E to the 0.036 times 5. When we plug that into our calculator, we get $4,788.87. So remember, when you have growth or decay that occurs continuously, you can use formulas that involve the constant E. For interest that's compounded continuously, we use A equals PE to the RT. And when we have continuous exponential growth and decay, we use N equals N naught E to the KT.